Hello, my name is Sam Chevalier, and today I will be telling you about our work entitled Accelerated Probabilistic State Estimation in Distribution Grids via Model Order Reduction. This work was done jointly with my advisor at MIT, Professor Luca Daniel, and our collaborator at the University of Padua, Professor Luca Scanato. Now, we all know that distribution grid loads are getting bigger, such, for example, electric vehicles, more variable, for example, distributed energy resources, and generally more uncertain. Now, state estimation is a tool which helps system operators overcome the associated operational uncertainty. However, when a distribution grid have pockets of poor observability, this can lead to a high degree of uncertainty in the solution of the state estimation problem. Now, in this paper, we construct a reduced order model of the nonlinear state estimation equations. This allows us to solve a so-called probabilistic state estimation problem much faster, where in probabilistic state estimation, you resolve a state estimation problem every time you sample from the load distribution. Now, in doing this, we expected a computational speedup of up to an order of magnitude over conventional methods. Now, in order to construct a reduced order model, we built an exact second-order expansion of the common nonlinear state estimation equations, i.e. power flow, power injection, and voltage magnitude equations. And the second order expansion had a constant term, a linear term, and a quadratic term. Next, we use so-called projection-based model order reduction in order to compress these equations. Now, we did this by first approximating our state x with some reduced order state x hat projected onto an orthonormal operator v, where this orthonormal operator comes to us from the model order reduction community, and we are able to dynamically expand this operator every time we solve a new state estimation problem. So next, we projected the nonlinear equations onto a subspace given as the product of a Jacobian and our operator v. And finally, this gave us a reduced order model, f hat of x hat. Now first, this new system is very small, so we're able to solve it very quickly using a Newton method. And second, as we update our operator v, we're able to dynamically expand and thus improve our reduced order model. In order to test our methods, we considered the 8,500 node distribution network, and we assigned two so-called uncertainty regions, where we assumed there were a subset of buses where we lacked real-time measurements. And instead, we assumed uniform distributions associated with each of these loads with bounds given by plus or minus 50% of their historical averages. Finally, we performed timing analysis by sampling 1,000 times from these uniform distributions and repetitively solving the state estimation problem. Now, in this plot, on the x-axis, we have the measurement profile associated with each new state estimation problem we're solving. And the y-axis gives us how long it took to solve the associated problem. Now, the red curve shows us how fast it takes a conventional method, i.e. Gauss-Newton, to solve the state estimation problem. And it takes about a quarter second for every new state estimation problem. However, our reduced order model solver is about 40 times faster than the conventional method, which is a really good speed up. Our full algorithm, though, has other computational bottlenecks, which make it only about 4 times faster than the conventional method, which is still a significant speed up. So in conclusion, we found that our reduced order modeling algorithm overall was about 4 times faster than the conventional method of Gauss-Newton state estimation with QR decomposition of the Jacobian. However, the reduced model solver at the heart of our algorithm was 40 times faster than Gauss-Newton. And this was actually a surprising result for us because we found that the primary computational bottleneck wasn't solving the reduced system, it was actually testing the result of the reduced system on the full order system, which is always a necessary step when you're dealing with a reduced model system. And this highlights a key difference between the power flow problem and the state estimation problem. Where in the power flow problem, your residual error is always going to 0, and you can use that as a test for convergence. However, in state estimation, the residual error is not necessarily going to 0, so it always must be projected onto a smaller subspace. And this procedure is inherently slow. Thank you very much for attending this talk.